Hi, welcome back. So today we're going to graph a rational function. If you feel like you're pretty set with this, I would say look at this rational function that we have, x squared minus 9 divided by x squared minus 5x plus 6. You can pause the video and try graphing that. And afterwards come back and follow along, either skip to the end or look at some parts in the middle, just skip around and just see do you know what's going on? If not, we'll just go through this problem together. As you already see, there's a lot written. That means that I made a big mistake all the way down here, and now I'm reading the problem. But here we go again. X squared minus 9 divided by x squared minus 5x plus 6. A rational function is a function where I have kind of two polynomials, two expressions being divided by one another. And the one on the bottom, the denominator one, has a variable. We could have it, the parent function, the most basic rational function is 1 divided by x. And you've probably seen it. It looks like this. But if you have it the other way around, like x over 1, that is just x. So it's not really like a rational function. And this behavior is something we'll see a lot with these equations. Step number 1. There's a lot of steps. I think maybe like 10, 12 steps. A lot going on, but I think it's pretty intuitive. You could split it up into certain parts. Part 1, the first half of the steps is gather all your information that you would normally do for a graph. And step number 2 is graph all the information, but we split into steps and I number it so that it is easy to kind of keep track of. So step number 1, we want to factor out numerator and denominator. Same thing as polynomial functions. We just want to factor it out and get to a point where you can find when it equals 0, both the numerator and denominator. Numerator, denominator. So factoring it out, I have x minus 3, x plus 3, divided by x minus 3, x minus 2. These are we see it's all factored out. Next thing, step number 2, I want to cancel out terms in numerator and denominator. I see I have an x minus 3 in both. Don't scribble out all the way. Don't erase it. I like to just draw a nice line through it, or you could group it together like that. But just some way to identify that I do have these matching terms. And now we do a lot of stuff with what's going on here. Step 3, whatever's remaining in denominator, whichever makes that 0 is a vertical asymptote. What I mean by this is we see in my denominator, I have my x minus 2 remaining. So I see what makes this 0. Because I need my function to divide by 0 to not exist. So a vertical asymptote means my function is not reaching that point. Asymptote means I'm not touching it. So therefore, if it can't exist at that point, I'm dividing by 0. So I'm setting this equal to 0 and solving that I do have x minus 2 equals 0. So x must be 2. Vertical asymptote is at x equals 2. And now there's a chain reaction. Once you do that, now you look back at what you canceled out. Anything that is canceled and not a vertical asymptote is a whole. If there was another x minus 3 over here, the x minus 3, that vertical asymptote takes precedence. But since there isn't another x minus 3 at the denominator, and I canceled out, I now see what makes that 0. X minus 3 equals 0, x equals 3. So I have a whole at x equals 3. Now I finish that and I see any remaining values in the numerator that is not a whole is a 0, root, or x-intercept. Those all have the same meaning in this context. So I have an x-intercept at x equals negative 3. I have a bunch of information already. Next up, we have horizontal asymptotes. does a horizontal asymptote exist? There's three main conditions, three main scenarios. You look at the degree of the numerator and denominator, and you see, is the numerator, is it greater than, is it equal to, or is it less than? So ignoring this for a bit, we'll just talk about these conditions. So if the degree of the numerator is greater than the degree of the denominator, that means that my numerator is increasing so much more. It's being so much stronger than my denominator. If it's so much stronger, then I'm like have a big number or like a big negative. It's a big value. So therefore I have no horizontal asymptote. There's no horizontal asymptote. My end behavior, it goes to infinities. Goes to infinities. Whether it's positive or negative infinity, it just goes to infinities. This is important to keep in mind. Like once you see this, you can now do your end behavior stuff that we did for polynomials, is make it go to infinities. It shouldn't go to an asymptote at all. Next up, if the degree of the numerator is equal to the degree of the denominator, your horizontal asymptote is at when y equals the quotient of leading coefficients. There's a lot of math terms here. And what I mean by this is if you had like negative 4x to the fourth, like plus whatever you need, and you have like 3x to the fourth plus like something else, and these are leading terms, you have a horizontal asymptote at y equals negative 4 divided by 3. Because it have the leading coefficients, negative 4, positive 3, and this is my horizontal asymptote. And finally, if the degree of the numerator is less than the degree of the denominator, horizontal asymptote at y equals 0. Looking up over here, I see x squared minus 9, x squared minus 5x plus 6. Square is my degree, 2, like degree of 2, degree of 2. So my horizontal asymptote must be at 1 divided by 1. They both have coefficients of 1. So horizontal asymptote for this graph at y equals 1. And now step 7 kind of snuck in here. We want to find the y-intercept, as in when does x equal 0. So I'm going to plug in 0, f of 0 equals 0 squared minus 9, 0 squared minus 5 times 0 plus 6 to give me negative 9 over 6, or negative 3 over 2. So I have a y-int at 0, negative 3 over 2, x-int at negative 3, 0, and a vertical asymptote at x equals 3. X equals 2. And I'll copy these two. X equals 2 whole at x equals 3. Writing it all down so that it's not all scattered. So I have all my information. Like I said before, the first half is information gathering. And now I pretty much have almost all the information I would need. But it's enough to start. Step 8. Step 8. Oh, it didn't let me copy it. 8. Graph asymptotes and intercepts. Let's do this. Make my big grid. And now I see asymptote at x equals 2. Horizontal asymptote at y equals 1. Y-intercept at negative 3 halves. So right here. 0, negative 3 over 2. And x-intercept at negative 3. Negative 3, 0. The whole is not graphed just yet. I have a hole at 3, at x equals 3, but we don't know where it is yet. And now at this point, I'm going to put it in the same line. What we need is we want to make a number line and identify signs like positive or negative. So you make your number line, and on your number line, you include your x-intercepts and your vertical asymptotes. And we test values in between all the sections that were made. So the values I want to test, I'll test 0, I'll test 3, I'll test -5. 0 is a nice value to use because you probably already found your y-intercepts if you have one. So I see that this is -3/2. F of 0 equals -3/2. So it is a big negative. And we do the same for the others. F of -5 gives me, and I personally like to plug into the factored form. Some people might find the original one easier, but I like to use a factored form. So -3 plus 3 minus 2. Rewrite over here, x minus 3, x plus 3 over x minus 3, x minus 2. So plugging in -5. -5 minus 3, -5 plus 3 over -5 minus 3, -5 minus 2. -5 minus 3, that's a negative. -5 plus 3, that's a negative. -5 minus 3, that's a negative. -5 minus 2, that's a negative. Negative times a negative is a positive. Negative times a negative is a positive. Positive times divided by positive is a positive. So it's, all these negatives give me a positive. And then finally, with 3, we do the same. F of 3 gives me, oh, you can't use 3. And that's a little mistake I made. Think about why you can't use 3 for a minute. What about 3 is special, and why can't we use 3? So what's special about 3 is it's a whole. And a whole would make this undefined, so I don't know if it's positive or negative. Because it's neither. It doesn't exist. So that's a mistake on my part. So you scrap that. And let's use 4 instead. So f of 4, 4 minus 3, 4 plus 3, 4 minus 3, 4 minus 2. Positive, 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 which gives me positive. So I have my signs. Now, with my signs, I can now plot on my graph, knowing that I must be positive in this section. I must be positive here. I must be negative in this entire section. This entire section must be negative. And this entire section must be positive. So I like to start from the points that I know. I must touch my x-intercept. I must touch my y-intercept. So starting from -3, I see going to the left must be positive, and I must get close to my horizontal asymptote. So I'm just going to go get close to it and flatten it out. That is my start of my graph. Part 1, done. 1 of 3 done. Part 2, I see I must go negative. And I must also touch this point. I don't know why it's a straight line, but I'm fine with it. I must go from -3 to -3/2, staying negative. And then I must stay negative. And I'm not going to my exit. There's no x-intercept here. So when you have an asymptote, you must stay on that side and just go to the infinity. So I'm just going to -infinity. And this is a point where a lot of students did make mistakes, where on the other side of the asymptote, I see it must be positive. So it must come from the positive side. I get close, and I have to go down to the asymptote. So this is a really tricky part. So I'll go through it one more time. Where I'm coming from an asymptote, a vertical asymptote, so I must come from the positive. Since I am positive, I must come from the positive infinity. Come down to like wherever you want to, like wherever you can see it. And I stay positive, getting close to the horizontal asymptote. So as I stay positive, get close to it, and just make a point right. This graph looks really, really gross. We see weird curves, some weird straight line. But that is fine. It is touching all the key points. And now let's actually see it on Desmos. So here's my graph on Desmos, where I have key points right here. And also, where are my asymptotes? At x equals 2, and also at y equals 1. Making these dotted lines so we can see a bit better. And we see I do touch these points. I am going to these asymptotes. I'm going to the negative infinity, coming from positive infinity. My end behavior my cyan line is just getting really, really close to an asymptote. So please continue practice. Use Desmos to check your answers. Use video as a resource. And that is... Oh, one last thing I forgot. I always forget this. I'm sorry. But hole. You must graph your hole. Honestly, for this graph, and what I should do is at the end of my paper, there's no end to this, so I can't redo it. I should always just write hole, so I could go back and graph it. So my hole is at positive 3. So at x equals positive 3, I'm just going to go to my graph, and this, I can't erase it without completely destroying it, so I'm just graph a hole. And that also appears in Desmos, where if I go to where 3 is, it is undefined, so there's a hole there. So that is now my final graph. My mistake, my bad. Hopefully you don't forget. So now let's fully recap what we have. You want to factor numerator and denominator, cancel like terms. You have a vertical asymptote, hole, zeros, and just making sure this. So that is my kind of rough idea. So let's actually go through it one more time. With your rational function, you first must factor it out fully. Then you cancel out any like terms, but not in a destructive way. You cross it out so you can still see it, because you still need to identify those values. Anything that wasn't canceled out in the denominator that remains is a vertical asymptote. Anything that is cancelled and not a vertical asymptote is a hole. Then anything that wasn't cancelled out in the numerator is a 0. So vertical asymptote has highest priority if that remains. Then you have hole, then you have zeros. Next up, we want to see, does a horizontal asymptote exist? You will have these values. Your reference sheet has this little description for you that will help you navigate horizontal asymptotes. We go through it. We see that this one, my degrees are the same. So I take the coefficients, 1 divided by 1, horizontal asymptote at 1. I list everything I know, keeping in mind my hole. So I just write it in bold at the bottom of the page, be like, don't forget this. And also you find the y-intercept. With this information, we plot these 4 things if you have them. Vertical asymptotes, horizontal asymptote, y-intercept, x-intercept. After you plot those, you make your number line using your vertical asymptotes of 2 and your x-intercept of -3. You find the signs in between these sections, in however many sections you have. Keep in mind, you cannot use the value of the hole. Once you find these values, then plot starting from these intercepts, because the intercepts must be where the function touches. So it must be positive from -3 to -infinity. From -3 to 2, it must be negative. And from 2 to positive infinity, it must be positive. Once you graph it, connecting all the lines, no big gaps except for where asymptotes are, you then put where your hole is. And that is all you need for rational functions. So please be mindful of finding out these values. And yeah, continue practice, do like one practice, make sure you have a good understanding of what's going on. Feel free to email your questions, and good luck.